Let us talk about analysis of recursive codes. So far we have talked about analysis of iterative codes. In recursive codes, what happens is a function calls itself. For example, here I have written a function fun that takes an integer value n. It returns immediately if n is smaller or equal to 0. In other cases, it prints GFG on the screen and then it calls itself for n by 2 and n by 2, right? So we need to know how much time this function takes, and it's not that easy. For iterative solutions, we just had to count how many operations we are doing in terms of input size. Here we do not have any loop sort of thing, or we do not have any direct way to count how many operations we are doing. So what we do to solve recursive solutions is we first write a recurrence relation. That's what we are going to learn in this video. So first we will learn how to write the recurrence relation in this video, and in the next video we will discuss how do we solve the recurrence relations. So how do we write recurrence relation for this? What we do is we assume that this function takes tn time for input value n, right? And then this function is making two recursive calls. So it's going to take tn by 2, right, plus tn by 2 by these two recursive calls. If it takes n time for input size n, then it's going to take tn by 2 here. Now, apart from these two calls, it's also doing something more, and all that work it is doing, it's constant amount of work. It's not doing any loop, it's not making any function call, right? So it's constant amount of work. So we can say theta 1, right? So this relation is true when n is greater than 0, right? And when n is smaller than or equal to 0, right, then what we have? We have tn equal to theta 1. It's a constant amount of work, because if that is the case, then we just return, right? So this is our general case, and this is our base case, and this can be rewritten as 2tn by 2 plus theta 1, right? That's what we can rewrite. I just added those two terms. And if n is to be considered as a positive value, then you can simply write that it's going to reach ultimately the value 0, and t0 is theta 1, right? That's our corner case or base case to solve the problem when n is greater than 0. So this is how we write the recurrence relation. This is our recurrence relation. This is our base case for recurrence relation. In the next video, we'll discuss how do we solve these recurrence relations. Here is an exercise for you. Please pause this video and try to write down recurrence relation for this function. So in this function, what is happening? Say if this function takes tn time, then we are doing tn by 2 work here, right? And all this is true when n is greater than 0, plus tn by 3 work here in the next call, and then we are doing this theta n work, right? So the recurrence relation is this when n is greater than 0. And when n becomes 0, or when n is smaller than or equal to 0, how much work we are doing? We are doing constant amount of work. So we can write t0 is theta 1, right? So that's the time complexity of, that's the recurrence relation for time complexity computation of this recursive function. Here is last exercise for you. Please take a closer look at this recursive function and try to guess the recurrence relation for this. And it's super easy. If this function takes tn time, then it's going to take tn minus 1 the recursive call, then it's going to take theta 1 work for all this condition check and printing, right? And when n is 1, then it's going to take theta 1 time. So this is the recurrence relation. So here we have learned how do we write recurrence relations. In the next video, we'll discuss how do we solve these recurrences.